is Ronnie Decker. I'm a registered nurse, and this is Nursing Analysis. Today, we will be talking about the electrical conductivity of the heart and action potential in the cardiac myocytes. To begin this lecture, we must first cover some key points in relation to how electrical conductivity takes place. We will start with action potential. Action potential is a rapid rise and subsequent fall in voltage across the cellular membrane with a characteristic pattern. When we discuss action potential here, we are discussing how certain cells in the heart are affected. These cells we will be discussing are the pacemaker cells and the cardiac myocytes. Pacemaker cells are specialized myocytes. They possess basic filaments and contract weaker than the myocytes. They work by initiating and conducting action potentials. The cardiac myocytes are contractile cells and contain a stored reserve of calcium. These cells are attached by intercalated discs, which link the cells together and define their borders. Intercalated discs are the major portal for cardiac cell-to-cell communication, which is required for coordinated muscle contraction and maintenance of circulation. Action potential in cardiac cells differs slightly from skeletal muscle cells in that cardiac cells contract longer to allow the blood to be pushed out of the heart. In a resting cell, the resting membrane's voltage, known as the resting membrane potential, is usually negatively charged inside the cell and positively charged outside of the cell. In order to understand how this resting state is achieved, we must discuss three different types of positively charged ions, where they are located and what amounts. These ions are potassium, calcium, and sodium. Each of these ions are found in varying amounts inside and outside of the cell. We will assign some random whole numbers for the amounts of these ions to make it easier to understand. Just think of potassium as being 90% inside of the cell and 10% outside of the cell. Sodium is 10% inside the cell and 90% outside of the cell. And calcium is 10% inside of the cell and 90% outside of the cell. So let's do a little math. On the inside, we have potassium at 90%, plus sodium at 10%, plus calcium at 10%, giving us a total of 110% on the inside. On the outside, we have potassium at 10%, plus sodium at 90%, plus calcium at 90%, giving us a total of 190% outside of the cell. So as you can see, there's more positive voltage surrounding the cell than inside of the cell. Most cells are initiated by the nervous system, the autonomic nervous system to be specific, including the sympathetic and parasympathetic systems. But when it comes to the heart, the nervous system is only able to increase or decrease the speed of the heartbeat. The nervous system does not initiate the impulse to make the heartbeat. The cluster of pacemaker cells that make up the sinoatrial node are found in the right atrium of the heart, and the sinoatrial or SA node is also known as the pacemaker of the heart. The SA node initiates all heartbeats and controls the rhythm and rate of the heart. If the SA node becomes damaged, other structures will take over this role. Those structures will be discussed later in this lesson. The SA node is autorhythmic, which means they can create their own action potential without nerve stimulus. They fire about 80 action potentials per minute, each of which stimulates a heartbeat, which equals an average heart rate of about 80 beats per minute. Pacemaker cells do not have a true resting potential. The voltage they possess starts at around -90 millivolts and moves upward until it reaches the threshold, which is about -45 to -55 millivolts. If you were to graph this with the x-axis representing time and the y-axis representing the voltage, it would appear like this. There are 5 phases of action potential in cardiac myocytes, phases 0 through 4. We begin with phase 4, which is known as the resting phase. This is when the voltage is stable in normal cardiac myocytes at about -90 millivolts. Then we move to phase 0, which is known as the depolarization or rising phase. Here, the sodium channels of the cell open and allow sodium to enter the cell, causing the cell to become more positively charged. Next is phase 1, which is also called the short partial repolarization or peak phase. The cell reaches its peak positive charge and then briefly repolarizes. This is due to negatively charged chloride entering the cell to slow the influx of sodium, and then the sodium channels closing and the potassium channels opening to allow potassium to exit the cell. Phase 2. This is known as the plateau phase. During this phase, the sodium channels close and the calcium channels open, allowing calcium to enter the cell. There will be a brief period where the potassium and calcium values are equal, causing the plateau or flatter curve on the graph. Phase 3. This is the falling or repolarization phase. The calcium channels close, stopping any further calcium from entering, and then the sodium-potassium pump sends 3 sodium ions back outside of the cell and allows 2 potassium ions back into the cell. This will return the cell back to its resting potential. Now we must talk about the pacemaker potential. The pacemaker potential is seen in cells in the SA and AV nodes. It differs from the action potential of the cardiac myocytes in that phases 1 and 2 are absent. The heart displays autorhythmicity. For example, denervated heart, such as the heart of a cardiac transplant patient, continues to contract spontaneously. As mentioned before, pacemaker cells do not have a stable resting action potential, and it is the spontaneous depolarization of the pacemaker potential that gives the heart its autorhythmicity. The pacemaker potential is produced by a decrease in membrane permeability to potassium, a slow inward current because of calcium influx via T-type or transient calcium channels, and an increased sodium current because of sodium-calcium exchange. Once the threshold potential is reached, L-type calcium channels open, calcium ions enter the cell, and depolarization occurs. In contrast to the cardiac myocyte action potential, there is no inward movement of sodium ions during depolarization. Repolarization, which is phase 3 of the action potential, occurs because of an increase in potassium permeability. At the SA node, Potassium permeability can be further enhanced by vagal stimulation, as in the vagal nerve. This has the effect of hyperpolarizing the cell and reducing the rate of firing. Sympathetic stimulation has the opposite effect and increases the rate of firing. We will now move into discussing the electrical conduction system of the heart and learn its pathways. Everything starts at the SA node, which is located in the right atrium. The SA node initiates an electrical impulse, which then branches out to the Bachmann's bundles in the left atrium of the heart. This impulse stimulates the atria to contract. The impulse continues to follow the internodal pathways to the atrioventricular or AV node. The AV node is located in the interventricular septum and slows the impulse to allow the ventricles time to fill with blood. If damage occurs to the SA node, the AV node can take over pacemaker responsibilities. The rate of impulse is slower here and discharge on an average of 40 to 60 times per minute. As we continue to follow the impulse, we see that it then travels down to the bundle of His. The bundle of His divides into the left and right bundle branches, one for each ventricular wall. The bundle branches further divide into Purkinje fibers, which are located within the muscle tissue of each ventricle. The impulse then signals the ventricles to contract. If damage were to occur to the SA node and AV node, the bundle of His in its left and right branches can also take over pacemaker responsibilities, but the rate of conduction here will be even slower, averaging about 30 to 40 beats per minute. So, to review, the SA node controls the rate of contraction for the entire heart muscle because its cells have the fastest rate of spontaneous depolarization. This means they initiate action potentials the quickest. The action potential generated by the SA node passes down the electrical conduction system of the heart and depolarizes the other potential pacemaker cells, including the AV node, so that it initiates action potentials before these other cells have had a chance to generate their own spontaneous action potential, forcing them to contract and to send the electrical impulses at the pace set by the cells of the SA node. This is the normal conduction of electrical activity in the heart. Before we end this video, here's a fun, quick review that might make it a little easier to remember the electrical conductivity of the heart. It is essential to start this sequential with action potential. Pacemaker cells and the stories they tell, beginning the signal that causes the reaction of the entire heart and its contraction. Next in line, a friend of mine, the muscular cells that encase calcium wells, shining the light on the cardiac myocyte, entering each other with speed that is brisk through the connection of intercalated discs, various volumes of ions at large begin entering the membrane to change its charge. Each cell contains specific channels, and only certain ions are members of this panel. The membrane is our friend, controlling what goes in, doing what they are told until they meet the threshold. Sodium begins to climb, peaking out the line. Chloride makes it stop, and the line begins to drop. Calcium begins to grin, for it is now time for it to enter in. Potassium runs away, for inside it can no longer stay. As this essential sequential reached its action potential, we can say we did our best. Now it is time for the cell to rest. The channels will close, the action is froze. There is still the restoration of ions we must trace, and how they are put back in their place. Run, skip, or jump, restoration is accomplished by the sodium-potassium pump. We shall now start the electrical art that begins in the heart. We begin with the sinoatrial node in signal mode down the internodal road. Bachmann's bundle is part of this ride on the left atrial side. This allows the atria to contract and the signal to get back to the atrioventricular pack. The AV node has a slower mode for its road as it casts will, allowing the ventricles to fill. It holds everything still. To Mr., to Ms., to her, no his. The biggest bundle of all, traveling down the septal wall. Into the ventricular muscles, the signal will fall. Now the signal can go no lower or higher as it meets its fate in the Purkinje fibers. Contraction is this reaction, returning the heart back to relaxing. Yes, this is true, by half at a time, adding to the theory with a couple more of these rhymes. The work of the heart as a whole is never complete. That is why there are two parts to every heartbeat. Thank you for taking the time to learn with nursing analysis. Please like and subscribe to enable the future production of educational videos and content.